Alright, from this lecture we start our study of integral calculus. Probably in high school you might have learned integration as an inverse operation of differentiation, so that you first studied indefinite integral. Definite integral. Then, based on that, you study definite integral, which can be used for calculating the area under the curve, for example. But here we first define definite integral as the calculation of area. Then we move on to indefinite integral. So because this way it's easier to generalize the notion of integration to higher dimensions, although in this lecture we only treat one variable integration. There are actually a few different ways to define integrals, but the one we use here is called the Riemann integral. Riemann is a German mathematician of the 19th century. But before that, we need to define some building blocks to define this Riemann integral. And the first is the partition of an interval. Partition of an interval. So we consider an interval from A to B. And of course, A must be less than B. Okay, and we define a finite sequence, let's call it delta, xn, such that A is equal to x0, and which is less than x1, which is less than x2. So this is an increasing sequence. And xn minus 1 and xn, which is equal to b. So basically, if we have this interval from A to B, including both A and B, we make some points. So a x0 is equal to A, and x1, x2, and so on. And xn is equal to B. Okay, and each of consecutive values, elements of this sequence can make a closed interval. Let's say x0 to x1 and x1 to x2 and so on. So in general, xi to xi plus 1. So each of these is called a subinterval. Subinterval. And the mesh or the norm of this partition. Oh, okay. So a partition, by the way, is the sequence. Okay. So this sequence itself is called the partition. This one is called the partition, and the mesh or the norm of the partition is the maximum length of the subinterval. Okay, max xi plus 1 minus xi, where I varies from 0, 1 up to n minus 1. Okay, so these subintervals are not equally spaced. Some subinterval may be greater than other subintervals, and so on. So we take the largest of them and call it the mesh or the norm of the partition. Now let f of x be a bounded function? Bounded function on this interval between a and b. And we define the following quantities. So capital M I is the supremum of the value of f of x within the subinterval xi and xi plus 1. And lowercase mi is the infimum of the values of f of x within the same subinterval. Okay, if this function f of x is continuous on this interval, then the supremum and infimum are maximum or minimum or within the respective subintervals. But this f of x may not be continuous, but we assume this is still bounded. So the supremum and infimum can be always defined. So there is no problem in the definition of this mi, capital Mi and lowercase mi. Then furthermore, we define the following quantities. Lowercase s delta. So this delta signifies the partition of the interval between a and b. Okay, so this is defined as the summation from 0 to n minus 1, and these infimums times the length of the subinterval. And capital S delta is defined in a similar manner, but we use this capital M. So that is supremum times the length of the subinterval. Okay, and the first one, this is called lower Riemann sum. Riemann sum. And the second one, this is called upper Riemann sum. With respect to partition delta. With respect to partition delta. So delta appears here. So this summation, these two sums, depend on how we partition this interval. Okay, so if we choose different partitions, then the values of these sums will be different. The meaning of these sums can be understood more intuitively if we draw the graph of this function. Let's say we have this function from a to b, and we have a partition. Okay, so each of these mi times xi plus 1 minus xi represents a rectangle, the area of a rectangle, right? So let's see, this is xi plus 1. So maybe this is not a good example. Let's see, we have this function like this. So here the infimum would be somewhere here. Okay, so this value will be infimum, the value of lowercase mi, and this value would be uppercase mi. So that's supremum, and this is infimum. Okay, so in the first sum, the lower Riemann sum, each term will represent this area. Okay, so that is below the curve made by the graph of f of x. Okay, and the upper Riemann sum corresponds to this area, this yellow region, this rectangle. Okay, so this means the area under the curve of this Riemann this function. Okay, that will be let's see, this region. Will be somewhere between this lower Riemann sum and the upper Riemann sum. Okay. However, in general, this function can take negative values. So in that case, we would have something like this. So in that case, we would have so this value would be the supremum, and this value would be the infimum. So this area is actually signed area. If the value of the function is negative, then this area will be negative value, but the absolute value would correspond to the real actual area, but it has a sign. Okay, so still this case is that's less negative, and this is more negative. Infimum is more negative. So in any case, we have the lower Riemann sum is less than or equal to the upper Riemann sum. So this holds generally. Next, we would like to refine a partition. So here's the definition of refinement of a partition. So let's say if we have one partition like x0, x1, and so on up to xn, and suppose we have another partition, let's call it delta prime, that consists of x0 prime, x1 prime, and so on, and xm prime. So the number of elements of delta and delta prime are different. So if we look these partitions as sets, then if delta is a subset of delta prime, so that means each of these elements in delta corresponds to one of these elements in delta prime. So if this is the case, then we say delta prime is a refinement of delta. Okay, so this means if we have a partition between A and B, so let's say we have these partitions, then if we have a finer partition like this, okay, so red ones corresponds to delta prime, and this is good. So the yellow ones corresponds to delta. Okay, let's say. So every point in delta corresponds to one of the points in delta prime. So in this sense, delta prime is a refinement. So it gives a finer partition than delta, but it also includes delta. So this means if, let's say, xi xi plus 1 is a subinterval of delta. So this comes from delta. Then, so this xi corresponds to some xj prime. Okay, and this xi plus 1 corresponds to some let's say j plus k prime of delta prime. But between xj prime and xj plus k prime, there are some more points in delta in delta prime in general. So we might have points like xj prime, xj plus 1 prime, xj plus j plus 2 prime, and so on, and xj plus k prime. So we have more subintervals between these 2 points. Let's see a more concrete example of refinement. So suppose we have an interval between 0 and 1. Okay, and let's say delta is a partition of this interval. So for example 0, 0.5 and 1. This is a partition of this interval. Let's call it I. And let's say delta prime is 0, 0.2, 0.5, 0.7, 0.9, and 1. This delta prime is a refinement of delta. So this 0, 0 corresponds to this 0, 0.5 corresponds to this 0.5, 1 is 1. But there are additional points like this, and this. Now, if we have a partition delta, then we can define the lower Riemann sum and the upper Riemann sum of delta with respect to delta. And if we have its refinement, delta prime, this refinement is also a partition of the interval, so we can define the corresponding lower and upper Riemann sums as delta, uppercase S delta, and so on. Now we have this important lemma. So delta prime, let delta prime be a refinement of delta, and delta is of course a partition of some interval, and f of x is a bounded function, so that these Riemann sums can be well defined. So bounded. Then we have this inequality. The lower Riemann sum of delta is less than or equal to the lower sum of delta prime, and the upper Riemann sum of delta is greater than or equal to the upper Riemann sum of delta prime. So this means if we refine our partition, then the lower Riemann sum becomes larger, greater, and the upper Riemann sum becomes smaller or less. Okay. Okay, let's prove this. First of all, let's define a subinterval I of delta. Let's say xi to xi plus 1. Okay, this is a subinterval of delta. And also we choose a subinterval ij prime. Let's call it xj prime to xj plus 1 prime. This is a subinterval of delta prime, such that not just any subinterval, such that this the latter subinterval is included in the former interval. Okay, so this is like this. So if we have a subinterval xi plus 1, so xj prime is somewhere between this j prime and xj plus 1 prime. Okay, and let's see, then define mi as the infimum of the values of f of x, where x is in this subinterval, and mj prime is defined to be the infimum of the values of x, where x is within the subinterval ij prime. Okay, and we should see that this mi is less than or equal to mj prime. Why? Because this former subinterval covers a wider area, right? A wider range of values. So if x is something like this, then the infimum is infimum mi is at least as small as the infimum of within this range, ij prime. So if actually the minimum, the very minimum within this subinterval ii is also within this interval ij prime, then that would be this will be equal sign. But otherwise, mi should be less than mj prime, because minimum can be somewhere here, which is outside the interval ij prime. So let's say if xi corresponds to xj prime and xi prime I plus 1 corresponds to xj plus k prime, then we have the following equation: mi times xi plus 1 minus xi. So this is a term involved in the lower Riemann sum, right? So this should be equal to mi times sum of L from 0 to k minus 1 and xj plus L plus 1 minus xj plus L prime. So this is, we just split this interval into these subintervals because delta prime is a refinement of delta. So this is possible. So we put this my inside the summation. Xj plus L plus 1 prime, xj plus L prime. And using this inequality, we have this inequality. m j plus l prime. Okay, and then we sum both sides, this and this, over all possible i's. So then we have on the left hand side the lower Riemann sum with respect to delta, and on the right hand side the lower Riemann sum with respect to delta prime. So this one is proved, and we can prove the inequality for the upper Riemann sum in a similar manner. So I will just skip it and you should try yourself. Now, based on this lemma, consider a sequence of partitions, actually, which are refinements of previous partition. Okay, so delta is a partition, and delta prime is a refinement of delta, and delta double prime is a refinement of delta prime, and so on. So we keep refining these partitions. Okay, so for each of these partitions we can define its corresponding lower Riemann sum and upper Riemann sum. Okay, so after each refinement, the lower Riemann sum is greater than or equal to the previous Riemann sum, the lower Riemann sum. So this lower Riemann sum keeps getting greater and greater. On the other hand, the upper Riemann sums becomes less and less. Okay, and so on. And so we have an increasing sequence of the lower Riemann sums and the decreasing sequence of the upper Riemann sums. Okay, and the lower Riemann sum is bounded above by the upper Riemann sum, right? So therefore, this supremum of the lower Riemann sum exists. So this supremum is taken for all possible partitions, delta. Okay, so we vary delta in various ways, then take the supremum. Okay, so this supremum exists, and so this is due to the continuity of real numbers. Okay, and this upper Riemann sums, it is bounded below and it's decreasing, so we this infimum also exists. So infimum of the upper Riemann sum and the supremum of the lower Riemann sum, they exist, and we have this inequality. Okay. Based on this observation, we finally define the notion of definite integral. Okay, so again, let f of x be a bounded function and defined on this interval between a and b, including both a and b. And let lowercase s delta and uppercase s delta be the lower and upper Riemann sums. With respect to delta. Yes, and delta is of course a partition of this interval. Okay, and we say f of x is Riemann integrable. or simply integrable. Integrable. If infimum of, supremum of the lower Riemann sum is equal to the infimum of the upper Riemann sum. Okay, so in the previous explanation, so we always have this inequality. So if this equality holds, then we say this function is Riemann integrable. Okay, and if this is the case, then we write this sum as this integral from a to b f of x dx. So this is defined to be the supremum of the lower Riemann sum. Or equivalently, this is the infimum of the Riemann sum, the upper Riemann sum. Okay, so this is definition. Okay, so this is the definition of this definite integral. If all these definitions seems too obvious, let's consider the following counterexample of Riemann integrable functions. Okay, so let's say f of x is defined on this interval between 0 and 1 such that it takes the value of 1 if x is a rational number and 0 otherwise. So that means if x is irrational, then f of x is 0. Okay, in this case, for whatever the subinterval is, let's consider this subinterval. Okay, then let's say it's I. Okay, then the infimum of the value of f of x within this subinterval is what? So it should be 0, right? Because however small this interval is, there are always irrational numbers in there. So the infimum should be 0. And the supremum of this function within this interval should be 1, because again, rational numbers are dense everywhere. So there are always at least one rational number in this interval, in any intervals. So its supremum should be 1. And if we take the Riemann sum, both lower and upper, then any lower Riemann sum should be 0, because all infimums are 0, right? Any upper Riemann sum should be 1, because the upper supremum is 1, and we are summing over this interval, so the length of this interval is 1 and the height is 1, so the sum is 1. Therefore, this applies to any partition delta. Therefore, the supremum of the lower Riemann sum is 0, which is of course less than 1, and 1 is the infimum of the upper Riemann sum. So therefore, this function defined by this is not Riemann integrable. Now let's see some basic properties of Riemann integrals. First of all, the definite integral is essentially the signed area. So if we have a function like this, and interval is between this and this, let's say a and b, then then the integral is basically this area. It's signed in the sense that it can be negative here. For example, here's negative. So let's say if we have 3 points A, B, and C, so this integration from A to B is the sum of two areas. So that is this area and this area. So from A to C plus C to B. So this should be obvious. And also, if A is less than B, we adopt the following convention. So integration from B to A. In this case, B is actually greater than A. So instead of integrating in this direction, we are integrating in the opposite direction, so to speak. So this is defined to be negative of this integral from A to B. Now dx is here. Okay, so this is, consider this as a definition. And also this proposition should be almost trivial from the definition of the Riemann integral. And let's say f of x and g of x are bounded functions, I mean integrable functions on this interval between a and b. And let k and l be any real numbers. These are constants. Then the new function k times f of x plus l times g of x. So this is a new function defined as a linear combination of these two functions f and g. This is also integrable. And the value of this integral from a to b, k f of x plus l g of x. So this integral, the value of this integral becomes k times the integral of f of x plus l times the integral of g of x. Okay? So the integral of a linear combination of two functions is a linear combination of the two integrals. Okay, so this means the operation of integration is a linear operation. Okay, so here we go again. It's a linear operation. So far we have seen many examples of linear operations. You know, this integration is a linear operation, and we have seen differentiation was also a linear operation, and also taking limits is a linear operation. Okay. Anyway, let's continue. And we have seen that not all the functions are integrable, but we have the following very strong result. So this is a theorem. We do not prove it here right now, but we will do it later. So if a function, let's say a continuous function on some interval, a continuous function on this interval is integrable. on the same interval. So if you know a function is continuous, then we don't have to worry about its integrability. It is integrable. We will give the proof for this theorem later and move on to the next theorem, which is known as the fundamental theorem of calculus. Fundamental theorem of calculus. Okay, so let f of x be a continuous function on an open interval. Let's call it I. Okay. And let a be a constant in this interval. Constant. And for any x in this interval, f of x is integrable because it's continuous. Integrable either on a between a and x or x and a, depending on which is greater than a. A or x. When x is greater on this interval, when x is less than a on this interval. Either way, f of x is integrable because it's continuous. Then let's define a function capital F of x by this integral from a to x and f of t dt. Okay. Then this function capital F is differentiable on this interval I, and f of x is differentiable on this interval, and f prime, so the derivative of capital F is equal to lowercase f of x. Okay, so this is called the fundamental theorem of calculus, and this connects differentiation with integration. More specifically, you can see the operation of integration is an inverse operation of differentiation. Right? If you integrate this function, then you get this function, and if you differentiate this function, you get the original function back. So differentiation and integration, they are inverse operations of each other. Let's prove this theorem. So what we need to prove is actually this. So based on the definition of differentiation, capital F x plus h minus fx over h. This limit should converge to lowercase or f of x. Okay, and from the nature of integration as the area, or as the signed area we have in this numerator here, minus f of x as integral from a to x plus h, and from a to x, and this should be equal to integration from x 2x plus h. Okay, and now let us define the following quantities. Lowercase m as the minimum of the values of f of x, f of t, where t is between x and x plus h, including both x and x plus h, and capital M as the maximum value of the function in the same interval. Okay, you should note that we are using minimum and maximum rather than infimum or supremum. This is because first of all, we are dealing with closed interval, and also this function is continuous. Therefore, we can use, instead of infimum, minimum, or instead of maximum, instead of supremum, we can use maximum. Okay, and we can choose lowercase s and uppercase s within this interval, such that f of lowercase s is lowercase m, and f of uppercase s is equal to uppercase m. Okay, so this is due to the extreme value theorem, if you remember. Because f is continuous and this interval is closed, so there must be some value of s and lowercase or uppercase s that satisfies this equation. Okay, then we have lowercase m times h. So this is the signed area of a rectangle with height m, which could be negative, and the width of h. Okay, let's see, this is less than or equal to this integral, and which is less than or equal to the area of this rectangle. So basically what we are doing is this: we have an interval between x and x plus h, so this width is h. Okay, we have this function. Okay, the minimum value maybe somewhere here, maybe, and the maximum value is somewhere here. So this maximum value is m, and the minimum value is lowercase m, and the area under this curve is somewhere between the area of this smaller rectangle and this larger rectangle. Okay, so that's what this inequalities mean. Okay, so because of this, okay, so this integral is equal to wait a minute, this quantity, so this difference of these functional values. So therefore, if you divide both sides by h, we have f s and f of x plus h minus f of x over h and f of uppercase s. Remember the way we define this value. So this is equal to this m, okay? And this is equal to this uppercase m. Okay? Then we move h towards 0. Then we have this lowercase s must approach x, and also this uppercase s approaches x because this x h becomes smaller and smaller, and also f of x is continuous, so that means f of s approaches f of x and f of uppercase s approaches f of x. So that means both of these, this one and this one, they both approaches the same value, f of x. By the squeeze theorem, therefore, this middle value must also converge to the same value. So this must converge to f of x. So that was to be demonstrated. Okay, and the proof is done. Now that you know the definition of Riemann integrals, in principle, you can calculate the integrals of any functions that are integrable. However, in practice, it's not so easy. So there should be some easier way to calculate Riemann integrals. And for that, we first define this notion of antiderivative or primitive functions. Okay, let f be a function on an open interval. Okay, and let capital F of x be an integrable function, a differentiable function. On the same interval. Okay, then we say f of x is a antiderivative. Or primitive function. Function of lowercase f of x. So we say this if the derivative of capital F is equal to lowercase f. Okay, so if this relationship holds, then we say capital F is an antiderivative or primitive function of lowercase f. From this definition of antiderivative, we can see that if this is an antiderivative of lowercase f of x, then it is also true that any function of this form, f of x plus c, where c is a constant, is also an antiderivative of the same function, f of x, because if you differentiate this with respect to x, then it is also lowercase f of x, because the c will disappear when differentiated. In fact, the converse is true. So that is summarized as this lemma. Let f of x be a function on an open interval I, and let capital F of x be an antiderivative of lowercase f of x, then any antiderivative of lowercase f of x is given as capital F of x plus c, where c is a constant. Okay, so let's prove this. Let g of x be another antiderivative. Of f of x. Then we differentiate g of x minus f of x. Then the operation of differentiation is linear, as we have seen before. This will be g prime minus f prime. But both of them are, g and f both are antiderivative of the same function. So that will be this lowercase f of x minus lowercase f of x, which is 0. Therefore, the original function, this g minus f, must be a constant. Constant. And the proof is done. So there are actually infinitely many antiderivatives of a given function. And we call the collection of all antiderivatives as indefinite integral. Okay, so indefinite integral is defined to be a collection of all antiderivatives of f of x. So indefinite integral of a certain function f of x is the collection of all antiderivatives of that function. And for the indefinite integral, we write like this: integral of f of x. Here we don't have any values here and here, so it's just nothing here and here. So this is how we represent, we denote indefinite integrals. And also, if we have a constant like this, f of x plus c, in indefinite integrals, we have this constant, which can be anything, and we just call it constant of integration. And here's a rather trivial theorem regarding antiderivative. Let's say f of x is a continuous function on an interval I, open interval. Then f of x has an antiderivative on this interval, and the anti-interval is given by this: a integral from a to x of this function, where this a is any value from this interval. Okay, so this is an antiderivative of f of x. And the proof of this should be easy. To begin with, as this function f of x is assumed to be continuous, so we can define the definite integral of this function. And from the fundamental theorem of calculus, this function, capital F of x, if you differentiate this function, then we get the original function back. So it is indeed an antiderivative of lowercase f. And the proof is done. And in this theorem, we couldn't have chosen any other constant instead of a, in place of a. For example, if we choose b from this interval, and we could define another antiderivative defined by this integral from b to x. But from the property of integral, this is actually equal to this, x and t and wait a minute, a to it's b to a. And f of t dt, and this part is a constant, so we could just set it to some constant c. So in this case, we have f of x dt plus c, and that is f of x plus c, where this f of x is the one we defined before. This theorem has a nice corollary. Let's prove this. So we use the same notation, this f, which is continuous on this open interval I, and capital F, which is the antiderivative of this lowercase f. So if that's the case, we have this relationship. Integral from a to b of this function is equal to the difference of antiderivatives. Okay, and the proof is quite easy. So this right hand side is this integral from a to b. The previous x is replaced with this b. So f of t dt and plus some constant and minus this one, and integration from a to a. Okay, x is replaced with this a dt and plus the same constant. But this latter integral is 0 because it has same this interval contains only one point and the width is 0. So this is equal to 0, and this c will cancel. So after all, what's left is this part. Okay, so that is same as this integral. Now, of course, this variable x, in dx, and it's t and dt, whether it's x or t, it doesn't matter. This is a bound variable, so to speak. So we can use any symbols as long as it's not confusing. And the proof is done. The next theorem shows how to integrate by substitution. So it's called integration by substitution. Okay, again, let f of x be a continuous function. on some interval. Some, well, just don't specify it. And let's say x is a differentiable function. So x is actually a function of t, differentiable on, so it's a differentiable function of t, okay, on an open interval j. Okay, then we have integral of f of x is equal to integral of f of x of t times x prime, which is the derivative of x with respect to t, and integral dt. So integrate of with respect to t. And second, for any AB in this open interval J, we have integral of x of A to x of B. Remember, x is a function of t. And f of x dx is equal to integral from A to B of f of x of t times x prime of t dt. So this means, okay, so let's see part 1. This is the left-hand side is an integral of a function with respect to x. And the right-hand side is an integral of some function with respect to t. And that function is made of two parts. The first part is f of x of t, which is a composite function. And the second part is the derivative of the function within this composite. Okay, x prime is a derivative. Okay, let's prove this. Oh, by the way, this equality in part 1 actually means, this ignores some constants here because it's indefinite integral. So this is equal within some constants. Okay, so ignoring the constant factor, constant term, we say they are equal. Oh, okay, anyway. So let's prove this, and let's fix some a within this interval j. And for any t within j, let's define antiderivative of this function by this x of a to x of t and f of x dx. Okay, so we integrate f of x as a function of x from this value, f of a to x of a to x of t. Okay, then the resulting function is an antiderivative of f of x. Okay, and here x of t is considered as a constant value. Okay, so we are fixing some t. But this can be defined for any t, okay, within this interval. And then we differentiate both sides. And we can apply the chain rule. Differentiate both sides with respect to t. Okay, then we have f prime of x of t times x prime of t by applying the chain rule. Okay, but f prime is an antiderivative of f of x. So it should be f of x of t. And this part remains x prime t prime. So this shows this function on the right hand side, f of x of t times x prime of t, is an antiderivative. Sorry. The antiderivative of this function is this, capital F of x of t, viewed as a function of t. Okay, so this proves part 1. And part 2 follows immediately from part 1. It's just a definite integral version of part 1. So it should be easy. Let's see a few examples. First example is this. And let f of x be any differentiable function, then f prime of x over f of x dx is log modulus f of x plus constant. Okay, and of course we're assuming f of x should not be 0, right? So proving this is an exercise. Just apply integration by substitution, and this should work. Next, consider calculating the antiderivative of this function, calculating indefinite integral of this function, where a is not 0 and m is a natural number. Okay, and so let's substitute this part, ax plus b, as z. Then we have dx dz equals to 1 over a. So this integral becomes, let's see, 1 over z to the power of m and times 1 over a and dz, right? So this should be equal to, let's see, 1 over a and 1 minus m z to the power of m minus 1 plus c, if m is greater than or equal to 2. Or otherwise, it should be 1 over a times log z plus c when m is equal to 1. So that means the original integral should, then we just replace this z with ax plus b, and we have 1 over a 1 minus m and ax plus b to the power of m minus 1 plus c, or 1 over a log ax plus b plus c. So this is it. Next, consider integrating this function, x times square root of 1 minus x dx. So to integrate this, let's substitute t equals to 1 minus x, square root of 1 minus x. So if we square both sides, we have t squared is 1 minus x. So that means x is equal to 1 minus t squared. So dx dt is minus 2t. Therefore, this integral becomes, so x is 1 minus t squared, and square root of x, 1 minus x is t, and dx dt is negative 2t, so that's negative 2t and dt. So this integral is a lot easier to calculate because we can find the antiderivative more easily than the original integration. So anyway, this is equal to, if we expand everything, it should be, let's see, 2 times x to the power of 4 minus x squared dt. And it's easy to see that the antiderivative of this function is t to the power of 5 over 5. And similarly, the antiderivative of this is this, plus constant, of course. So let's simplify this a little bit. So that would be, let's see, 2 over 15 and t cubed and t 3t squared and minus 5. Okay, and let's see. So we have this and this. So use them. So that would be 1 minus x to the power of 3 halves and 1 minus x minus 5 plus c. So after all, we have and 3x plus 2 plus constant. So this is it. The next technique is known as integration by parts. It's based on the product rule of differentiation. So let f of x and g of x be differentiable functions. Not just continuous, but differentiable. On an open interval I, then we have integral of f of x times g prime of x dx equal to f of g times f of x times g of x minus integral of f prime of x and g of x dx. And second is the definite integral version of part 1. For any a, b in the interval, we have this definite integral from a to b, g prime, and f of x times g of x, and a, b. And of course, this part, this means this is equal to f of b times g of b minus f of a times g of a. So first substitute b and then subtract the one with x replaced with a. So this one. So let's prove this, and that is again we prove only part 1, and part 2 is immediate from part 1. So from the product rule, let's differentiate f times g with respect to x. Then we have this f prime times g and f times g prime. So if we move this part to the left and swap left and right, we have f times g prime equals to f of x g of x prime minus f prime g. Then we integrate both sides with respect to x, then we have this result, right? So if we integrate, we just get f of x and g of x, and this is just integral of this and integral of this. So it's done. Let's see a couple of example of application of this integration by parts. So here's the first example: x times cosine, hyperbolic cosine x dx. So how do we find this integral? So to integrate this, notice that cosine h is actually equal to the derivative of sine h, hyperbolic sine. So we regard this as x times sine h x prime. Then we apply, so let's say this is f and this is g prime. Okay, so from this we have, by applying the integration by parts, x and sine h x minus then derivative of this part, which is 1, and sine h. So 1 is just 1, so we get rid of this, and then this is easy to integrate. So hx, if you integrate this, you have cos x plus constant. Just in case you don't remember the definition, cosine h is this, minus x, and sine h of x is minus this. Okay. Next, consider this example. Let's define in as this integral, dx over x squared plus 1 to the power of n, where this n is a natural number. Okay. So first of all, let's note that this in is actually equal to x squared plus 1 over x squared plus 1 to the power of n plus 1. So we just multiplied both numerator and the denominator by x squared plus 1. So this is n plus 1, and extra term appears here. And if we split this summation, then we have x squared and x squared plus 1 n plus 1 dx plus dx x squared plus 1 to the power of n plus 1. Okay. Let's see. This is n plus 1. Okay. But this part is actually n plus 1 by definition, right? So if we replace n with n plus 1, we get this term. So we have x squared n plus 1 dx plus n plus 1. So this is a recursive equation connecting in with in plus 1 with some extra integral. Okay, so the next question is, how do we evaluate this one? So to do that, first note that this one, 1 over 2n x squared plus 1n. So if we differentiate this, we have x over x squared plus 1 to the power of n plus 1. Okay, you should check this. Okay, it should be easy using the chain rule. And anyway, so we want to use this, and so this integral becomes x squared plus 1 n plus 1 dx. So that is x times x over x squared plus 1 n plus 1. So here we go. We have this term here. Okay, so this x squared is split into this x and this x. Okay, so this one is a the derivative of this function. So this means, so we just substitute this expression, then apply integration by parts. We should have negative x. Okay, so this one times 2n x squared plus 1 to the power of n. And since negative sign is here, we have positive sign here. And that will be 1 over 2n coming from here. And integral. And this x will be gone after differentiation. And we have only this term left. Okay. But of course, this part is in. So now we have 1 over 2n in, so that's this term, minus x over 2n x squared plus 1n. So if we substitute this into this, we have we have after some manipulation, we have in plus 1. So we put this on the left hand side and the rest on the right hand side, and that will be in minus this integral, and that integral becomes this expression. So if factorized by in, it becomes 1 minus 1 over 2n times in and plus 1 over 2n times x and x squared plus 1 to the power of n. Okay. Now, when n is 1, then I1 is just this x squared plus 1, which can be calculated easily if you know that the derivative of arctangent is 1 over x squared plus 1. Okay, so this is the antiderivative of this function. Then if you know this, then you can calculate I2 by using this expression. Okay, so now you know when n is 2, this is 2 times 2, and I1 is this arctangent. plus constant, plus wait a minute, plus this function, 2 times 2 and x squared plus 1 to the power of 2. So this would be 4 and this would be 4. Then if you know this function, then you can calculate I3, I4, and so on. Lastly, rational functions deserve special attention. And first, consider polynomials as a special case. So let's say we have a function that is a polynomial of x. So an x to the power of n, an minus 1, x to the power of n minus 1, and so on. So a1x and a0. And of course, those coefficients, a1, a2, and so on, they are real numbers. Then if we integrate this, we have the following function. So this is easy to verify because if we just differentiate this result and we get this polynomial function back, and an minus 1 and x to the power of n and so on, a1 to x squared, a0x plus constant. Okay, sometimes we just ignore this constant term because it's too obvious. So this is easy. But what about rational functions? Remember, rational functions are made by ratio of polynomial functions, right? So it's like f of x over g of x, where f and g are both polynomial functions. Okay, if we integrate this, the result may not be a rational function. Okay, in the case of polynomial, the integral of a polynomial is a polynomial. Okay, this is a polynomial function. But in the case of rational function, the result may not be a rational function. But in general, it's a combination of, it's a sum of rational functions and logarithm and inverse trigonometric functions like arctangent. To see that, we need the following lemma, which we give without proof. Okay, so lemma, that is partial fraction decomposition. Okay, so this says any rational function can be decomposed into a sum of the following three forms. Okay, first, polynomials. And second, something like this. K constant over x plus constant to the power of n, where k and a are real numbers and n is a natural number. Okay, so this n is a natural number, and this n is a natural number. This k and a are real numbers. And finally, ex plus d over x squared plus bx plus c to the power of m, where e wait a minute. This B, C, D, E are real numbers, and M is a natural number. And also B squared minus 4C is less than 0. Okay? So this last term appears because we only want real numbers. Okay? We don't allow complex numbers to appear in this expression. So therefore, this looks like the discriminants of quadratic function, right? So if this holds, the roots of this quadratic form inside this parenthesis they are complex numbers, but we don't want complex numbers, so we just limit the form to be reduced up to this form. So if we have a rational function, let's say f of x, so this can be always decomposed into a sum of these. Okay, so that will be polynomials plus something like this. No, there can be multiple terms of this form. Okay, and also multiple terms of this form. Okay, so we don't prove this here, but we will use it to calculate integrals of rational functions. Let's see a few examples of partial fraction decomposition. First example is this: x plus 5 over x squared plus x minus 2. Okay, so first look at this denominator. X squared plus x minus 2 can be factorized as x minus 1 times x plus 2. So let's assume this rational function can be expressed as a sum of these fractions. Then if we solve this equation for a and b, somehow you should find out, you should have a equals to 2 and b equals to -1. Okay, and if you just substitute 2 here and -1 here and add them, you should have this as a result. Okay, so this would be the partial fraction decomposition of this function. Okay, so in terms of the lemma, we have two of these terms. Okay, no polynomials, no functions of this form with a quadratic form in the denominator. We only have this form in this particular case. As a next example, consider this function: x to the power 5 minus x to the power 4 plus 3x cubed minus 3x squared minus x minus 2 over x to the power 4 minus x cubed minus x plus 1. First, notice that the degree of the numerator is 5, whereas the degree of the denominator is 4. So we can do some division. In fact, this is equal to this: x plus 3x cubed minus 2x squared minus 2x minus 2, and this. So we have a polynomial here. Okay, and what about the rest? So we still have a quartic polynomial in the denominator, so somehow we want to reduce it. So x to the power 4 minus x cubed minus x plus 1. Actually, this can be, let's see, this should be let's see, okay, x cubed x minus 1 minus x minus 1. So we have x minus 1 as a common factor and x cubed minus 1. So which is x minus 1 times x squared plus x plus 1. So we have this decomposition. So this part, okay, let's see. This part should be decomposed as, let's see, ax plus b over this, and c over x minus 1 and d over x minus 1 squared. So we want to determine the values of a, b, c, d. So I leave it as an exercise to find these values. The answers are this: a is equal to b is equal to 1, and c is 2, and d is negative 1. Okay. So after all, we have the decomposition. So that is the given, wait a minute, where is it? So the given rational function, this one. Well, this one is can be decomposed into a polynomial and second form x minus 1 squared, and the third form. Okay, remember, so this, if you solve the quadratic form of this, the roots are complex. Okay, so we don't want that, so we leave it as this form. Okay. Now that we know how to decompose a rational function into partial fractions or polynomials, let's explain how we can evaluate the integrals of a rational function. So first of all, polynomials, they are easy to integrate. So there will be just polynomials, as we've seen before. And second, this form of integral, x plus a to the power of n, becomes this. So k is just a constant, so we can just get out of the integral. So this becomes this. First of all, if n is this n is greater than or equal to 2, we have k over 1 minus n times x plus a to the power of n minus 1. So that's when n is greater than or equal to 2. Otherwise, it will be log of x plus a modulus. Okay. So that's it. By the way, don't forget this modulus symbols, because logarithm is not defined for negative arguments, so it must be positive. To ensure that, we need modulus. And finally, consider this part, ex plus d and x squared plus bx plus c to the power of m. Okay, this is a little tricky, and remember we should have b squared minus 4c negative. Okay, this is important. We'll see why. So let's see. First of all, let's simplify the denominator. Okay, so x squared plus bx plus c. If you complete the square, we have x plus b over 2 to the power of squared, and plus c minus b squared over 4. Now, because of this condition, this part is positive. Okay, c minus b squared over 4. Because of this, it must be positive. So we can put h equals to the square root of this. Okay, so let's see. 4c minus b squared. Let's see. Square root of 4c minus b squared over 2. Then by putting this, okay, we have this equals x plus b over 2 squared plus h squared. Okay, then let's factorize everything by h squared. Then we have let's see, 2x plus b over 2h squared plus 1. Okay, and let's put this thing as z. Okay, then we have z squared plus 1. Okay, so z is 2x plus b over 2h. So if we substitute this into here, we have this, let's see, integral of ex plus d and x squared plus b x plus c to the power of m dx becomes this integral, e prime z plus d prime over z squared plus 1 to the power of m dz, where this e prime and d prime are the following. So you should try to derive these results. Minus 2, and d prime is minus be plus 2d over 2 to the power 2 times h to the power of 2m minus 1. Okay, so we can split this expression into this part and this part. So we need to calculate two integrals. That is, first, this one. And second, this one. Of course, m is a natural number. So first consider this one. Okay, in this case, it's actually easy. So we substitute z squared plus 1 as w. Then this integral becomes, so if you do this substitution, this integral becomes 1/2 dw over w to the power of m. So this reduces to part 2, right? So it's done. And for part B, for this one, we need to separate two cases. First, if when m is equal to 1, in this case, this integral is this, z squared plus 1. So that is arctangent, as we already know. Not x, it's z. Yeah. And when m is greater than or equal to 2, then it's a little bit different. But if you remember a previous example, remember this example? So this was solved by a recurrence equation. And that recurrence equation was this. So if we define in as this, in plus 1 was 1 minus 1 over 2n in, and 1 over 2n times, in this case, let's use the variable z, and z squared plus 1 to the power of n. So we know I1 was arctangent. Okay. So by using this recurrence equation iteratively, we can determine I2, I3, and so on, one by one, although we cannot find any closed form for this integral. In theory, it's possible to calculate it. And finally, here are some exercises for you. So you should validate the following integrals. So x plus 5 over x squared plus x minus 2 dx. So we did this example as an exercise for the partial fraction decomposition. Okay, so if you integrate this, you should have this log x minus 1 minus log x plus 2 plus constant. And another example, again, we also did this before as an example of partial fraction decomposition. Squared minus x minus 2 over x to the power of 4 x cubed minus x plus 1. So this integral should be this 1/2 x squared and log of, actually this is 4 over 3 x squared plus x plus 1. You know, we don't put modulus sign here because we know that this is always non-negative. And no, because the discriminant was negative, right? So, and the rest is arctangent. And 3 and 2 log x minus 1 plus 1 over x minus 1 plus c. Okay, so this is it. That's all for today.